Welcome to EDU World Space.
So for this question, we're told that a small particle has a charge of 5 times 10 to the minus 6 coulombs. And it has a mass of 2.00 times 10 to the minus 4 coulombs or kilograms. I'm going to fix this funny exponent. So this should be a 6. And it moves from A, where the electric potential is 200 volts, to B, where it's 800 volts. So VA is 200. And VB is equal to 800 volts. And the force is acting on the particle, and then this particle has a speed of so it's 5 meters per second at A, and then our goal is to get what is the speed at B. So I'll write that down. Oh, this is confusing. So this is little v at A is equal to 5.00 meters per second. And then our goal is to get little v at B equals question mark. So if we have a charge moving within this potential, let's see, I'm just gonna double check. Is there any other information about the potential? So is the potential changing linearly? Well, I guess you don't even need that information because of this sort of path independence thing. So for this problem, I think you want to more so use the principle that the change in potential energy, the magnitude of the change of the potential energy. Actually, we'll probably not use magnitude since we care about if it's losing or gaining. So, so the work done on a particle, I'll go back to that. The work done on a particle is equal, I guess there's a couple ways to think about it. So I'm going to think about it as there's no, I like to start off energy problems with the statement that W net external, so the net external work done on a system can contribute to a change in kinetic energy or a change in potential energy. So I'm going to say that the electric force is internal. So I'll say that this thing is 0. And so we get the equation that the change in kinetic energy is equal to minus the change in potential energy. And so let's go ahead and fill in either of these sides. So the change in kinetic energy, so it's starting at A, so it's 1/2 m v at A squared. Or sorry, it ends actually, so it should be change in kinetic energy is final minus initial. So you want to have its final state. So then that's going to be VB minus 1/2 v at A squared, and then that's minus the change in potential. So that's KQ final, or divided by R final. So forget this little line here. Minus the initial. So that's KQ over R initial. And so our goal is to solve for VB. So VB is going to be equal to, oh, I realized we don't even need this type of formula. That's just going to be So we just want to use the fact that U is QV. So actually, sorry, let me rewind a little bit given what we have. So so we want to use the formula that generally change in U is Q change in V. And so we can just say that change in U is Q change in V, and V final minus V initial. The final state is B. So it's going to be Q V at B minus V at, minus V at A. Great. So, okay, now we can solve for VB. VB, we just want to bring this to the other side. So bring that term to the other side, and then we get VB is going to be, so I know we'll end up multiplying everything by times 2 divided by M, and then we'll end up square rooting the whole thing. So that's just going to be 2 over M times plus 1/2 MVA squared minus QVB minus VA. Okay, and then now I'm going to go ahead and put this into a calculator. Okay, so when I put this into a calculator, I obtained that it was 7.416 meters per second.